Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We can get started now. It's a pleasure for me to introduce Stefan Wormlin. Stefan is a postdoc in the Computer Graphics Lab at the Swiss Federal Institute of Technology. Stefan received his PhD from the same institute in May of this year. Right? And he has done a lot of work in 3D video technology, also known as Free-Viewpoint video. Stefan?
Thank you very much, Stefan. So, hello everybody. I want to report on the 3D video activities we actually had over the last 3 or 4 years at ETH in Zurich. The presentation is entitled Dynamic Point Samples for Free-Viewpoint Video, because we use point samples as basic primitive to allow this Free-Viewpoint video. So what is Free-Viewpoint video actually? So if you look at this picture, Free-Viewpoint video uses multiple video streams to re-render time-varying scenes from arbitrary viewpoints. And this free navigation in space and time enables novel manners of interactivity. And this enables novel applications, for example, like freeze and rotate effects or instant replays. And what we use this technology for at ETH is basically for telecollaboration, just like you see in this image. Although this image is a little bit more in the future because technology on the projector side has to advance a lot to allow such images to happen. So 3D video is actually a very recent research topic, and so terms and classifications in 3D video are actually not defined yet. So if you look at this image, we call arbitrary 3D video. What you want to have from 3D videos, you want to have arbitrary setups of cameras, and you want to record what happens in rooms or maybe also outdoor. And then you want to be able to re-render the whole scene from arbitrary viewpoints, doing some view interpolation between the cameras. But typically, you can just scale that down and just bring them into different different topics actually. So one of these is stereo video, where you just have 2 cameras or 1 camera with depth information, and to that you get just a binocular stereo effect of maybe for your television or so. Then what actually you are also doing here at Microsoft is that Free-Viewpoint video with densely arranged cameras in parallel view. So that you need, for example, for 3D television scenarios, and also for freeze and rotate effects, for example. We at ETH are actually interested in the third topic here, which is Free-Viewpoint video from sparsely arranged cameras which are in convergent view. So we typically want to capture objects which are recorded in a room or so, and we want to re-render them from arbitrary viewpoints. And last but not least, there's also omnidirectional video, which can be seen as an extension of QuickTime VR to dynamic scenes. So you typically have a camera that looks around, and you get these panoramas, and they're moving over time. So our input data to most of our systems looks something like that. So this is basically 15 cameras, and one is just shut down actually. And you actually capture an object in focus. And you want then to be able to basically have smooth interpolations between these camera views. And here, for example, we have baselines about 2 meters or 30 degrees between the different cameras, and that's actually what we define sparsely arranged cameras, compared to densely arranged cameras where you only have 20 centimeters and stuff like that. This is actually an MPEG test data set which we provided for the Moving Pictures Experts group. Okay, here's the outline of my talk. I will first go into the context why we built such Free-Viewpoint video systems at ETH, because we have this huge BlueSea project which wants to build high-end telecollaboration systems. I will explain a little bit on the BlueSea technology, except for the 3D video system. Then I want to introduce this new primitive we actually have for our Free-Viewpoint video, which are dynamic point samples. And then I go into 2 different topics we have. The first one is the real-time 3D video system, which basically is used in this BlueSea system to acquire users in a cave-like environment and transmit that to another site to allow for collaboration. I will there focus a little bit on the differential coding aspects we implemented there. Then I will go into offline systems and present some of the work we did also for MPEG, where we actually also built an image space coding framework which allows free-viewpoint video with MPEG technology. Then I will conclude with a summary and present some future work. So the Blue Sea actually tried to build a novel telepresence system. We actually built at ETH two such portals. You see that on the two video images. We have one system that's a power wall, which is augmented with 16 cameras, and then we have a cave-like environment where we also augmented the system by 16 cameras. And the key idea here is that we want to record the user in real time, which stands in this cave or in front of the projection wall, and transmit this user in 3 dimensions to the remote site and re-render there the person, for example, here in the stereo display. So here you see basically that's Zurich, by the way, with the very beautiful lake. So we have 2 campuses at ETH. We have the old campus, which is located right in the city center. You see that over there, ETH center. And then we have a novel campus, which is more like US-like, which is situated on a hill outside Zurich. So the distance between these 2 campuses are 10 kilometers. Here's the system overview of the Blue Sea. So we wanted to build 2 distinct systems. We wanted to build a very complex, very high quality system, and then we wanted to build a very cheap and easy setup which you can maybe rebuild. So if you look at the left side, we actually have multiple, I have the laser pointer. So we have here, you see this is the cave. For the cave we need 3 projection units, so stereo projection units. We also have there some cameras. We have currently 16 cameras over there. Then, because you actually need some illumination which illuminates the person which stands in there, we have some active light in there which only gets on actually when we record some video images. And then one of the key novelties of this system is our shuttered projection screens. So basically what we do is we open up projection screens to look through the projection screens. And for such a short amount of time that you don't see actually that the projection wall gets transparent. And then of course if you have this highly complex system, you need to synchronize all the units together so that it works actually. So for that we have some synchronization. And of course if we need stereo display, you need some shutter glasses. And then what we do is we record the 16 synchronized video streams and process these 16 streams into a 3-dimensional representation which is based on point samples. And then we transmit that across to the other side and display that on screen. And the same is here, so we record also 16 video streams, we process them, we get 3-dimensional information, and then we re-render that here. As you see here, we have only 1 projector, so this is an active DLP projector, so it's much more easy, and we only need synchronization for the cameras and not for the whole system. Yep.
What's the frequency the projection screens are running?
They're actually running at 60 Hertz. Yeah. I will go into detail on the projection screens just on the next slide. I just skipped that. So this is actually just how it looks in the Blue Sea. So this is the cave environment. And actually what you see here is just for demonstration uses. So we can open up these projection screens. These are actually a liquid crystal inside the glasses, which allows us to just directionalize the molecules inside so that they can get transparent. And these are actually conference room displays, so such like that one, so which you can use for getting privacy in conference rooms. And nobody ever did switch these screens actually at 60 Hertz. And they're basically just, I mean, that's the limit. 60 Hertz really the limit for that. But actually, we just record video in each 7th frame because we cannot handle 60 Hertz video images. So we just have, right now we have 10 Hertz or something like that for video acquisition. And here you see how the timing looks like. So we just augmented traditional stereo actually by a 3rd phase. So in the 3rd phase, you actually close the shutter glasses of the person which stands inside. And as you see, somewhere here. Then we trigger the cameras, open up the projection walls, and capture some images for only a couple of milliseconds to get to the user. And because we do that at such a high frequency that the person which stands in this cave actually doesn't see that he gets recorded. Yep.
The constraint is that you differentiate between the recording and the projection. So all acquisition is without any projection.
No, actually what we do is, as it's pointed out here, so we you have typically these two phases in a stereo system where you project one for the left eye, an image, and one image for the right eye. And then what you can do is you can just move these pulses a little bit more together so that it gets an overlap on your shutter glasses. And in that small time frame, we actually just shut down the projectors. So we have a similar display in front of the projectors where we can just varying between transparent and opaque. So when we acquire images, we shut down the projectors, and then we get a trigger. We put a trigger on the video cameras so that we can then acquire an image, and so that we get some illuminated person, because typically in a projection setup we just have a dark room. So that's why we need some active illumination, which is done on LED basis. So we have there 10,000 LEDs inside there to illuminate the person for just this 4 milliseconds. Does that answer your question? Or this is actually an image we get out of the system. As you can see, it's pretty dark. So this is mainly due to that we just have this 4 milliseconds for acquisition. So since we want to have geometry in the whole system, we need some geometry reconstruction algorithm. And we currently use a shape from silhouettes method, which implies that we need some background subtraction algorithm. And we just use a classical background subtraction algorithm and do some post-cleaning to get then such silhouettes like that. Furthermore, we also use some color calibration method that we get homogeneous color over all 16 cameras, just like Hans-Peter pointed out. We use a similar method to achieve that. That's basically the difference between the second and the third image. And that's actually how blue sea looks like. So here, a female person is standing in the blue sea, and we acquire this person with all 16 cameras, and she can experience herself in full 3D. So she can move there, and she can just have, we have a tracker in there, a classical tracking device, and can just move around. But for this video, we just moved by ourselves. And that's actually the quality that you get out of this system. So the quality is not that high because, as you saw, the images are quite dark, so it's quite hard to get decent texture quality out of this system. Cameras are 640 by 480, so NTSC resolution right now in this system. So now I move on to the whole 3D video technology, because that's what I implemented or designed during my thesis. Of course, there are other people involved in this huge project, so we are, I guess, 15 researchers in the whole project over 3 years. And some of them just built the hardware, the synchronization unit, some of them just built applications. The core team in the computer graphics laboratory actually built the 3D video system and the whole communication layer between the two portals to allow this coding, this real-time encoding of the data. I guess who of you are familiar with point samples actually in graphics? There are a couple of? Okay. So as you may know, at ETH, almost everybody has to do point samples at some time in the career. So we also did some point samples. But I guess for our application, point samples are a very good primitive, because you don't need connectivity. That means that you don't need to encode connectivity, time-varying connectivity over time. So here we just can have these point samples and we can just stream them over a network channel. Furthermore, why we call them dynamic point samples is that we actually keep a correspondence of each point sample in 3D space to a certain pixel in the video camera image. And that's because we actually want to do some coding on a regular grid, because that's much more easy than to do that in 3D space, like with the point samples. And so what our geometry reconstruction algorithm actually does is we just, for each pixel in a video camera, we actually project that pixel into 3D space and get there a point sample. And that means that we have different attributes of the point sample which need to be extracted from a geometry extraction algorithm. And that's mainly positional normal information. As I said, point samples have some advantages over other representations. So one that's very good for us is actually that's a unified geometry and appearance representation. So topology changes like you have in this Free-Viewpoint video systems where you want to acquire time-varying scenes are just for free basically, because you don't need to handle these topology changes. And then, since it is a geometry-enhanced representation compared to image-based approaches, it typically needs less acquisition cameras for even broader viewing ranges. So right now we have 16 cameras and we can have arbitrary viewpoints on a half hemisphere actually. And by having this correspondence to the image space coordinates, we can have efficient coding schemes at our disposal, for example, by using just conventional video coding algorithms. So this, now I want to go to the real-time Free-Viewpoint video system, which is actually employed in this BlueSea software system. And two of the main features we have is that first we have an efficient coding scheme which works actually in real time, so real-time encoding and decoding, and it's based on some differential prediction we do on an operator basis. And furthermore, because 16 cameras are hard to handle in real time, so we need some control over which cameras are actually required for a certain viewpoint on the remote side. That's why we have a feedback channel which comes from the other side and tells us where actually the viewpoint is. And furthermore, we also say how big the person is on the remote side, so that we can just have a certain sampling of the representation. And this system, of course, can be used in telepresence applications like we do, or it can just be used for 3D video conferencing. Here's the pipeline of the real-time Free-Viewpoint video system. So first we acquire some images, synchronized multi-view video streams. Then we perform this background subtraction I just laid out. And then by extracting this polygonal approximation of the silhouette, we can then compute some three-dimensional information of each pixel. Then we perform this differential coding framework I will just show on the next slide to just cut down the shape computations and cut down the bandwidth we need for this system. And on the remote side, we basically just have to render these human inlays using a point splatting method. And of course, since these are geometry primitives, we can just combine it with any virtual scene which is common to such virtual reality applications. So the differential coding scheme we implemented works on the principle of operators. So we have three types of operators which are a little bit inspired by particle modeling actually. So we have inserts which add new point samples to the representation on the remote side. We have deletes which remove point samples. And we have update operators that correct appearance and geometry attributes of each point sample, which are already part of the representation, but whose attribute actually changed with respect to prior frames. And since we have this correspondence to the image plane, we can derive all these operators directly in image space. So insert and deletes are basically just can be seen on the silhouettes of the person, so the silhouette will change, and so each point on the silhouette that vanishes from the object in the foreground just gets deleted, and so forth. So here's an example of this. So on the left side you see an image at time step t, and in the middle you see an image at time step t+1. And then we apply this prediction operation in image space, which gets you the red regions which are actually deleted. So these are pixels which then become point samples which get deleted. We get green regions which are inserts, so new point samples are inserted into the representation. And then all other pixels which remain in the representation can potentially have some color information that changes, or also, of course, some positional information that changes. And we do that also in image space. As I said, 16 cameras are hard to handle, so we have implemented some dynamic camera control. So we actually distinguish two types or three types of cameras. So we have texture active cameras. And these are cameras which actually perform this differential coding scheme and thus get points or put point samples on in the representation on the remote side. And then we have reconstruction active cameras. And these are cameras which are needed to extract geometry information for each of these cameras. So as you see here, for one texture active camera, which is the green one here, so you can imagine that you have a virtual viewpoint which sits just like in a small range of this green camera. And then you need four, for example, additional cameras which contribute silhouette information to this green camera. And then in the current setup for a virtual viewpoint, we currently use 2 or 3 such texture active cameras. They are depicted here in yellow and in green. And what you see here is that if you use these 3 cameras, then you have maybe half of the cameras are really active, and the rest of the cameras are just passive and do nothing at all. Here are some results of some real-time 3D video streaming we did. So we currently can maintain 25,000 3D point samples at 9 frames per second. This is actually given by the BlueSea system. We currently use or need 3 to 5 megabits per second to transmit this whole 3D video stream. The system has an inherent latency because we do some pipelining of the different stages, so we get 3 to 5 frames latency. So which means that we typically have between, so at 9 frames per second we have 300 milliseconds to 500 milliseconds latency in the whole system. And as you see here on the bandwidth chart, the operators are actually color-coded. You see that here. So there are some peaks in the bandwidth, which are mainly due to camera handover. So you can imagine if you move your virtual camera to another place, at some point one camera gets texture active, and then you have to sample the whole frame actually. And this is one of these peaks. Here's an evaluation I did on these positional update operators. As you can see on the different images on the bottom, this positional update, which I didn't go into detail actually, gives us some block-based artifacts. You can see that here. So we can set a threshold for this positional updates. This threshold is actually in meter because we have a calibration that does metric calibration. So this means basically that for each pixel, we just tolerate an absolute difference in consecutive frames of 4 centimeters. And of course there on the right, this is 5 millimeters, so the representation is much better. Here on top you see some results for intermediate views. So this is basically 2 texture active cameras and just the virtual camera just right in the middle between these 2 cameras. If you look at quality versus performance between these different thresholds, this is actually Pearson R values, so from video coding, because since we do this coding scheme in image space, we can of course compare this on a video basis. So as you can see, the Pearson R values are actually quite good. But of course, if you go down with the positional update threshold, you get a lot of more bandwidth because you need to stream all these update operators. And here's a chart which shows that this actually brings something. I mean, you could also imagine that you can just get rid of all this coding scheme and just transmit each pixel in each frame. And that's actually what's done up here. So this is actually the point samples we can maintain here in this test scenario. And here you see the different charts of the positional update threshold, and says how many point samples we need to update in each frame. So as you can see, if you use this 4 centimeter threshold, you just have to update one quarter of all the point samples which are in the representation. course, you also have to do that on the colors, because we also do some color updates. And there, we just use another threshold which says what is the absolute difference between the different color channels. We currently actually use RGB here, so it's not that good, but that's more historical. So right now we would do that in YUV space. But this says that we accept certain tolerance of 16 intensity values on R, G, and B. And as you can see here also on the different images, of course you get some errors if you put that threshold up. But as you can see on the next chart, of course the bandwidth gets down if you allow more differences, of course. One other thing is actually that these positional updates are not only for the bandwidth requirements, so a nice feature, but it's also that if you have to calculate three-dimensional information for each of these pixels in each frame, that's also a processing bottleneck. So with these positional updates, we actually can also cut down the shape computations in this system, which is quite which is needed actually in this real-time scenario. And here's also a video with results. This is now a session between the different campuses at ETH. So the videos are actually not synchronized because that's quite hard to do over 10 kilometers. So this is actually one of the acquisition cameras, and the person stands in there. And here you see what another person sees on the cave walls. And there you see that we get some artifacts because of this differential coding scheme. So it gets some ghosting artifacts actually. Furthermore, we also get some artifacts because of the segmentation, which is not always perfect. And that's also why we want to move on to another geometry extraction algorithm, which is not relying on segmentation masks. But overall, the quality looks okay, I guess. If you have questions on the real-time thing, or else I would just move on to the offline system. Yeah.
Well, the linkage between points and texture.
Yeah.
So I got that in the pipeline. So it's more extracting silhouette. So when do you get back to linking?
So actually, what we do, we have these texture-active cameras, and these texture-active cameras apply this prediction scheme. And for each pixel which is in the foreground, we actually calculate the depth value by using silhouettes from the other cameras. Okay? And then we project this pixel with the depth information into a point sample. But we currently do that just on the rendering side. So we transmit basically pixels or multi-channel video images or something like that. And on the remote side, we just project them into space and just use point splatting to get some decent pictures. Yeah?
Are you actually rendering two different images for left and right eye?
Yeah, we do that. But you get that for free if you have three-dimensional information. I mean...
Yeah, once you get the... But you're rendering the points in a specific...
Exactly,
spot, though, right?
Yeah.
So, but you're not rendering a different set of points for the left and the right eye?
No, because they're not so...
They're pretty close, yeah.
They're pretty close. So in our setup, that, I mean, yeah, you get the same active cameras for both eyes. But of course, if you would move closer together, you maybe want to have different types of cameras for your eyes, actually.
What do you mean? Like, if you're like in the cave, how do you change like how the person viewing it is moving? What angle you're viewing it at?
So right now we just use magnetic tracking.
Okay.
So it's like a space mouse. I don't know if you're aware of such device. I guess so. So it's just a magnetic mouse which gives you some three-dimensional information on where this mouse is, and then you can move forward, and then, or you can just rotate, and then the whole scene gets rotated. Further questions? So we also built a recording system just like you have here at Microsoft. So we did that in 2002, I guess, was the first project we had this in, and it was a spin-off of the Blue Sea project. And actually what we built is we built an efficient processing pipeline also for this sparsely arranged cameras, and we also reconstructed geometry-enhanced Free-Viewpoint video just like with the same primitive. So this primitive basically goes through all our projects. And here we use this correspondence between the point samples and the pixels a little bit more, because we actually build a whole system which just uses video coding tools just like MPEG-4 or MPEG-2 and allows for this Free-Viewpoint video playback. And for that we also built a player which actually we called it full-featured, because it's a traditional recording player, so you can just have slow motion, you can have regular playback, you can have fast forward. But also we implemented a virtual trackball, which is common to computer graphics applications, so that you can rotate around the object. And such type of pipeline has some applications in multimedia streaming, just like for MPEG, and of course 3D visual effects or virtual replays are here good application scenarios. I talked about this player, so this slide basically says what interaction possibilities we get from 3D video compared to 2D video. So if you look at 2D video, what everybody has in his home, you basically have playback and you have pause, you have fast forward and stuff like that. And you actually get the same from 3D video. So you can implement the same there. You can just have multi-rate playback, you can have pause for freeze and rotate effects, stuff like that. But what you get more is you get just rotation, you can zoom, you can have really arbitrary viewpoints in this spatiotemporal space. And furthermore, what's also interesting for us is that you don't have only 2D display, but you have 3D display capabilities, because you have this geometry enhanced data at your disposal. So we actually built a data representation for this whole recording pipeline, and we actually brought that into the Moving Pictures Experts group. That's actually why I'm here today, because just in the convention center there's an MPEG meeting, and there we just extended traditional depth image-based representation, which are already part of the standard of MPEG-4, and augmented this data by not only using depth images plus color, of course, but also use additional information which helps us to allow for high quality display of point sampled representation. Because point sampled representation are very similar to depth image based representations, except that they have a little bit more geometry information. Like for example a normal, for each point sample you have to have a normal at your disposal. And furthermore, you have to have some information on the density, how many point samples I have in a certain volume. And this version 2 representation we brought there in is actually right now adopted as an extension of the MPEG-4 animation framework extension. And this allows us to do some efficient coding in image space. So we can encode the whole scene's visual appearance in multi-channel multi-channel video images by just using this depth information, normal information, etc., etc. And then on the player side, we can exploit the notion of dynamic point samples to allow for high quality display of this multi-view video data. And as I said, all channels describe color or position or such attributes for discrete point samples in 3D space. That looks somehow like that. So you have this multi-view video data, so each of these blocks are actually one camera. So in our setup we have 16 cameras. And for each camera, for each video image, we have these different layers or different channels. So of course we have color, 3 channels for color. We have 1 channel for position currently because we use depth information. Then we have, for example, 3 channels for normal information in each direction. And we have an additional field which we call splat size, which gives us some density information on the point sample geometry. And these different channels look something like that. So of course we have color, then we need to have a silhouette at our disposal, because most of our coding, or our own coder actually, just does some video object coding and not full frame coding. And then we have position, like depth maps. We have some normal information, you see it here, and then we have these splat sizes. And with this representation and with this primitive, we can actually build a whole image space pipeline for Free-Viewpoint video. So you need to have a system that actually can record multi-view video sequences and store them to disk. That's the first thing you have. Then you process this whole data to get you additional attributes for each video image. So for us, that's of course depth and silhouettes and whatever you need. And then you can actually just use MPEG-4 or AVC, which is a novel codec from MPEG, to encode that data, and then of course to decode that data in real time and bring that to screen with a point splatting method. Now, we talked a lot about what do we need for free viewpoint video in terms of video coding. So a traditional video coder, just like Windows Media 9 or so, is actually optimized just playback in the front fashion. So you just have regular playback in the positive time dimension. But for free viewpoint video, we actually want to have everything. And furthermore, we need to have some random access capabilities of each frame, because we have to switch between different cameras. So that's what actually is outlined in this slide. So you can see here, for example, this is a traditional MPEG-style prediction scheme. So you have an iframe, which is the red. So are you aware of video coding a little bit? Okay, so you have a traditional iframe here, and then you have some p-frames, for example, here. P-frames are predicted frames which are basically just rely on the last frame. So if you have 1 second per each iframe, you get to have 25 p-frames in between, which all rely on the last p-frame. But of course, there are more sophisticated approaches. So you can have b-frames as well. B-frames are actually don't only predict in the back, so they also predict to the front, yeah. And then, of course, you can also imagine, yeah.
The arrows are the wrong way around if you.
These.
Yeah, that's B-frame.
Yeah, you're right. You're actually right. But I just wanted to just depict some of the concepts. But you're right, you're wrong, yeah. But also you can imagine also a spatial temporal coding scheme where you just use nearby cameras to predict some information on your reference camera. So that's actually what's here. So this is the camera dimension. So these cameras are actually predicted from another camera. So that's actually what I guess you do here as well. But if we now come and just say we want to have a virtual viewpoint, and we want to have it like that. So this is of course then the space dimension. This is the time dimension. We want to have a path, a virtual viewpoint path in this thing. Then if we look at the different viewpoints we have to decode, then you see that, of course, in the beginning this is okay. This is also okay because you just need to decode 2 frames. But as you can see, if we now switch over, we just have to decode all these p-frames to the iframe and also decode these p-frames to the other iframes. So we get different decoding complexity for different viewpoints. And that's actually not that what you want. So you actually want to have just a smooth decoding complexity. So that's why we actually implemented a video coding scheme which gives you random access on each frame in each time step. That goes, of course, on and on. But I guess you get the thing. So we actually came up with a certain classification of free viewpoint video recording systems. So if you would use just traditional video coders, you would get something like we called constraint free viewpoint video. So that means that if we decode data on just small viewing angles between 2 cameras, for example here, this gets everything smooth. But if we move over one of these boundaries, so we need an additional camera, we maybe get a glitch or something. So we get some discontinuities between the frames. But if you can live with that, okay, then you can just use MPEG-4 tools. But if you want to have such a thing, this is unconstrained free viewpoint video, where you just want to move around in the spatial temporal area, then you need some random access capabilities. So here are some requirements or goals we set to ourselves on our own video codec for free viewpoint video. So we want to have multi-resolution so that we can have the target bitrate held constant. So we need a progressive coder actually, just like JPEG 2000 or so. Then we want this random access in space and time. So that means that we need to have multi-rate, because that's also nice for slow motion effects and so. And we want a constant time access to each frame in the whole bunch of data. Then since we employ this point sample framework, we need to have a coder that can cope with multi-attributes. So we don't only can have a coder which can only compress color information, but it should also compress normal information or depth information. And then we also want a coding framework which can handle view-dependent decoding, so that only the stuff gets decoded what's really rendered. We came up with a video coding framework which we called average coding. So I have to say, I mean, this average coding is solely for Free-Viewpoint video, so I guess you don't want to have that in Windows Media Player, so because that's really targeted to this Free-Viewpoint video approaches. So actually what we do is we take temporally averaged information as the reference frame that you can see here. So we take a bunch of frames and we just temporarily average all this data in this channel and build a reference frame out of this. Then we encode this reference frame. And then for each delta frame, we actually just take the difference between the reference frame and the original frame and encode this difference. And of course, what we wanted to do is actually that the delta frame has less information, of course, and gets better encoded. But since we have only this reference frame and each of the delta frames is actually can individually be decoded from the same reference frame, we have constant time access to each of these frames. For color, this looks something like that. So the average frame looks actually somewhat funny. So this is the thing here on the right, and this reference frame can actually not be used for rendering. So it's not like in the traditional iframe where the iframe can be rendered as well. So this reference frame is just additional information. You have to distribute the data of this average frame over all delta frames to get a decent bandwidth. But as you can see here, we just apply a silhouette mask on this average frame. And as you can see, this image looks quite nice. But of course, we need the silhouette at our disposal on the decoder, so we have to encode and decode the silhouette information in a lossless fashion. But we need that anyway for our point sample framework, so for us that's not an additional overhead. And then we can just stream detailed coefficients of the delta frame to get a more decent image quality. And of course, this not only goes with color, this also goes with depth information. This looks something like that. And it also performs even better on depth information than on color. We currently use ECW for the delta frame encoding, so we get this wavelet coefficients which you can just stream and chop off at some point. We evaluated this coding framework against other standardized coding frameworks. So we compared it to MPEG-4 with shape adaptive, with the shape adaptive coder. We also changed the MPEG-4 coder to allow intro-only coding, so that we get also multi-rate and random access, which we maybe want to have in our Free-Viewpoint video systems. Then, of course, our average coding framework has also multi-resolution capabilities. And then there's, of course, also JPEG 2000, which has multi-resolution capabilities because it's also based on a wavelet coder. And the JPEG 2000 also features full frame coding, which is not possible with the average coding framework because the data which we average is not good anymore if we do that on full frames. And here's some results for color information. As you can see, MPEG-4 outperforms all other coders. So MPEG-4 with motion compensation is just the best you can get. But of course, this is only good for constrained Free-Viewpoint video coding, but not for unconstrained Free-Viewpoint video coding. Then of course, MPEG-4 intro-only coding does have features for unconstrained Free-Viewpoint video coding and still performs better than our own coder. But if you need or if you want progressivity in your system, then average coding performs better than JPEG 2000 because it gets you some time prediction into the whole system. And this is the same thing for depth information. the funny thing here is that actually intra-only coding in MPEG-4 performs better on depth information than MPEG-4 with motion compensation. And this is mainly due to all this prediction stuff they have in there. These are optimized for color information and not for depth information. And we assume, although we did not evaluate it, that it's for normal information and additional attributes even worse comparing these two. And as you can see also is that average coding performs slightly better than JPEG 2000 on the depth than on the color information. And here's some rendering results from our coding evaluation. So the top row is actually uses 512 kilobits per second in each camera. So we currently use 2 cameras to render, so you have to double this number. On the bottom row, you see 128 kilobits per second. So this gets you approximately 300 kilobits per second, where you can just stream this whole Free-Viewpoint video to your player. And then on the columns, this is JPEG 2000, and you see here, JPEG 2000 has severe problems at this bit rate. And what you also see is that MPEG-4 with motion compensation just is the best actually you can get, also in terms of rendering. If you look at the differences,
You're using MPEG-4
alpha channel coding?
Yeah.
Yeah.
Okay.
I mean, that's
the full MPEG-4.
That's full MPEG-4. Yeah.
Right.
And you see, especially here, because our own coder and also JPEG 2000 gets some problem with the boundaries. Because there you have these high frequencies, and it just doesn't perform that well. And here, with the shape adaptive thing in MPEG-4, you just get the block artifacts, but nothing more.
So in JPEG 2000, is there actually an alpha channel codec?
No.
So you're actually providing that yourself?
No, actually, we just do some padding, but nothing more in JPEG. I mean, we just use padding in our own coder, and we just take the same images and put them in JPEG 2000. So we do some padding, but nothing more, because we don't have alpha coding in JPEG 2000.
You're not including the binary mask bits in this code?
No. I mean, this is also the data. I mean, the bit rates are just the binary masks are just optional here, because we need them at the decoder as well.
Okay.
But it's I guess 20 kilobits per second per camera. So in terms of bandwidth here.
Okay.
As you see here, I mean, JPEG 2000 on the depth images has some severe problems. And that gets then reflected on the final image, because when the depth information is not that good, here's actually the rendering is just in an intermediate view, also in the middle of 2 cameras. So if the depth information is not good, then actually the rendered image doesn't get good, of course. And here's also a video with results. So on the bottom left, you actually see interaction we perform on the player to allow these different interactions. So this is freeze or pause, so it is freeze and rotate effects. Then you get play, regular playback. Slow motion is with the double point. This is reverse play, reverse slow motion, stuff like that. These red dots are actually the contributing cameras we visualized for this thing, but it's not that good visible. This is slow, this is fast reverse, stuff like that. I can just play one more. As you see, we have some problems with concavity. So when this Korean guy just moves something like that, we get some problems with the shape from silhouettes method. So then you get some false projected point samples, which are then maybe projected on the torso with the color of the hands or stuff like that. But nevertheless, we can have here arbitrary viewpoints on the whole hemisphere. So we also have top cameras, which look from the top. So we have really the full spectrum here, 360 degrees. So I'd like to conclude now. We presented some real-time Free-Viewpoint video pipelines, which are employed in the Blue Sea software system. If you come to Zurich, you can gladly drop by and look at the system by yourself. You have there a differential update scheme introduced with these fragment operators, these update position, update color operators. And we also included a dynamic camera control to cut down the shape computations and also the required bandwidth we need for this real-time free viewpoint video system. And then we also have a free viewpoint video recording system with an efficient coding framework which solely which tries to fit all the data in image space or in video images. And we then get some nice playback features like random access or progressivity, and we have view-dependent decoding. So what do you want to have in the future? So if we really want to have free viewpoint video as a product or something like that, then you really want to go into high quality free viewpoint video. So this, in my opinion, is medium quality. So what you guys do here is really high quality. So this really looks good. So maybe then you just need better blending of the point samples. You need better mapping techniques to include it in this scenario. But furthermore, what's also interesting is also to capture scenes, because of course, in the Blue Sea system, we just wanted to capture the objects, the humans that are standing in this cave. But if you want to have just the multimedia or 3D video streaming system, then you want to capture scenes. And we think that we want to also have some geometry extraction algorithm in there which can cope with sparsely arranged cameras, not densely arranged cameras. And we believe that we can maybe use some structured light techniques which are invisible, that's ISL, so invisible structured light, to give us some depth cues actually for these sparsely arranged cameras. And we can then maybe augment this system with stereo algorithms and use this structured light technique to give us some clues to guide the stereo process. Of course, we have to go a little bit more into the spatiotemporal coding, because when we really have the whole scene at our disposal, we really have some multi-view video coding algorithms which need to be developed for this whole system. And actually MPEG right now investigates some multi-view video coding techniques which maybe are of interest to you. And of course, if you want to have free viewpoint video a little bit more to the market, then you also want to have some authoring tools which allow you to modify this free viewpoint video objects or whole scenes. And there you really go into spatio-temporal editing of scenes, and then it gets quite hard to what interaction you really want to have on these scenes to allow a decent authoring of this data. Of course, I did not do all by myself, so I have to acknowledge a little bit of people. So of course, the whole Blue Sea team, we're a bunch of 15 people, and a lot of students did some of the implementation of this work. That concludes my talk. Thank you.
So currently, how do you do the blending?
Right now, we just use standard point blending algorithms, so we don't use any information of how good this point sample is or how much it contributes to the final view. So we just take these 2 or 3 cameras and we just put them together in the first place. So we have like shells, point shells we call them, and we just put them together. And then we just use the point splatting technique is a sort of blending. So it blends only what's in the neighborhood of each other. So if you have a point sample that's in the background, it just doesn't get blended to the front point sample, because the point splatting framework handles that for yourself. But except for that, we don't do sophisticated blending right now.
So it's not weighted.
Point splatting do some blending regarding the normals, how they look and stuff like that, compared to your viewing angle. But except for that, no. But I guess it would be interesting also to get something like an uncertainty for each point sample, where you can just say how good this point sample is and stuff like that. And then you can include that very easily into the point splatting framework. But you have to estimate this.
Any other questions? Let's take the speaker again.